In this demonstration, I would like to introduce the normal distribution. The normal distribution was discovered by Carl Friedrich Gauss, who was a German mathematician, and it's a bell-shaped distribution, and it is a symmetric one. And a normal distribution or Gaussian distribution is most widely used in statistical analysis of experiments and of any kind of data. So from experimental point of view, overall, the symmetry of the distribution suggests that there is an equal probability to get a slightly higher value in an experiment, and there is an equal probability to get a slightly lower value, and the values are distributed in a symmetrical fashion as we get away from the mean value, the central value. So this property suggests that at some point the binomial processes with very large number of trials, they will also converge approximately to this symmetrical Gaussian distribution. And this also suggests us about the experiments when we get the data from instruments. So if the data from the same experiment is symmetrically distributed, like the Gaussian distribution, it means the system or the sensor is functioning properly. The probability density function of this distribution is given by this mathematical expression. So it's a complicated one, as we will see that its analytical integration is not possible through simple one-dimensional methods. Okay, so it is 1 over 2 pi square root sigma in the denominator, and exponential of x minus mu squared over 2 sigma squared. This is the first distribution in which the mean value and the standard deviation, they are appearing explicitly in the expression. The probability density function is in units of 1 over sigma, which are the inverse units in which we measure x value. Like every continuous distribution, the cumulative probability that the value of x is greater than or equal to xi. This is the cumulative distribution function, and it must be calculated by the integration of the probability density function from minus infinity to xi. So this suggests that the cumulative distribution function is graphically the area under the probability density function curve. So this is the procedure with which we will calculate the probabilities. However, the approximation to this integral is provided in terms of tables, and they are based upon the numerical integration. There is a standard variable transformation of Gaussian distribution. So we define a new variable z equal to x minus mu over sigma. So this transforms the distribution to a new scale of variable z, and the probability density function then becomes 1 over 2 pi square root and exponential of minus 1 by 2 z squared. So this suggests that this new distribution is going to have its mu value at 0 and sigma value equal to 1. And this distribution is going to be normalized, like as we calculate the area from minus infinity to plus infinity, the integral settles at a value 1. Okay. So let me demonstrate the procedure for calculations. So okay. So our procedure for calculation will be that from our data, our variable x is distributed normally about a mean value of x, and there is a sigma value in the x domain. However, with our standard transformation, z equal to x minus mu over sigma. So the new variable will transform the center of z equal to at 0. So it means mu of z distribution will be equal to 0 and sigma will be equal to 1. So therefore, our calculation strategy will be from x variable to z variable, and then we will calculate the probabilities, and then we will transform back for our interpretation to x. So we define the probability phi z, where z is less or equal to some value zi, and it is equal to the integral from minus infinity to zi value of the transformed density function e raised to the power minus z squared by 2 dz. So actually this cumulative distribution function in z, this will give us equivalent results for f of x, where x is less or equal to xi, and this will be equal to our calculation phi of z is less than zi, where the relationship between zi is xi minus mu of x over sigma of x. So this is going to be our transformation, which will help us to develop the estimates of probability using the z distribution tables. So okay. So this is the similar thing that I have explained, that probability a z value is between minus infinity to z. It will be represented by phi of z. It is the integral, and it represents the area under the probability density function uh, below the z distribution. So this is the function, normal distribution function, probability density function g of z. And if we plot the cumulative distribution function, so we know that it is a for every distribution, it is a monotonically increasing function which saturates at probability equal to 1. So this is the probability distribution estimates table. So this is from Professor William D. Corsi's book. So it's a 2-page table. So table A1, cumulative normal probability. So it takes on the values of z and provides the probability. So the each value in this table each value in this table, for example, this value is actually a cumulative probability. It is for phi of z value. So, and it suggests the area under the curve from minus infinity to a particular z value. So, given a z value, we will get the probability value. And likewise, if the probability is given, which means the area under the curve is given, then we can get the uh, corresponding z value. For example, right now, if I trace this value on the horizontal scale, so it is minus 2.8 somewhere here, and here at the top the delta z is written. So this is point minus 0.05. So the z value is up to 2 decimal places, it is 2.8, and the delta z value, it will add, so minus 0.05. So it means the given value is, we are reading is at minus 2.85. So this is the z value. This is the z value. And for a z value, we can then transform it to our original variable x. So that's going to be our process. So the first page gives us the values from minus 0 to minus 3.7. So it means if I look for the value at 0, so minus 0 and 0 minus 0.0, so the value is 0.5, which means the 50% probability region has been covered, and it is from minus infinity to a z value. So this value is very nice. So that's fine. Okay. So I was trying to highlight this value. So this value suggests that the 50% of the data belong to minus infinity to a value which is 0. The next page provides the values of probability beyond 0. So these are the positive values, and we can see the z values given in a vertical array, and the horizontal array at the top, it labels the delta z value, which is the increment to z to the second decimal place. So for example, if I'm interested in probability, so if I'm interested in a probability value, say phi of 0.54. So the first digit I have to see 0.5, which is here. So I have to look for 0.5 right here. Okay. So 0.5 value is here, and the second digit is somewhere here. So therefore, I will trace up to here, and this is the value which is the probability at a value 0.54. So we can read that it is 0.7088. So it means the area from minus infinity to that particular value is 0.7088, and this is the pictorial representation of that one. So it says that this table gives you the value of probability as the area under the curve from minus infinity to the z value. So on the next slide, there are two further examples. So for example, if z value is minus 2.87, so how do we figure it out? So we have to see the corresponding table. So I will trace from this line minus 2.8, and then from here the increment to the second decimal value minus 0.07. So the required probability value is 0.0021. Similarly, if we look for the value 0.072, so 0.7 and 0.02, so the value is 0.7642. So we have learned how to read the probability distribution table and the standard variable. So the problems related to normal distribution, they are transformed to the z variable. So the problems in x variable with a mean value, and a standard deviation, they will be converted for probability estimation to a z variable. And then with the z variable, we will use the probability distribution tables. We use the probability distribution tables, and we will get the probability estimates, and then we will utilize them in our interpretations. So I stopped this first. I have completed the first demonstration about the use of the probability distribution table for calculating probabilities, and from probabilities to the original variable x calculation. So the first, from probability, we will get to the z value, and then from z, we will use this transformation to get to the x variable. So we will continue our discussion in the second session.